Constitution of Alloys Introduction. Welcome to an in-depth exploration of the fascinating world of alloys. From the robust steel in our buildings to the intricate components in our electronics, alloys are the backbone of modern engineering. But what exactly are alloys? And how do their unique properties arise? In this video, we'll delve into the fundamental principles governing the constitution of alloys, uncovering the secrets behind their strength, durability, and versatility. Solid solutions, substitutional and interstitial. At the heart of many alloys lies the concept of a solid solution. Imagine a perfect crystal lattice of one metal, and then introducing atoms of another element into that lattice. When the solute atoms replace the solvent atoms in the crystal structure, we have a substitutional solid solution. This typically occurs when the atoms are of similar size and have similar electronegativities. Think of brass, an alloy of copper and zinc, where zinc atoms substitute for copper atoms in the crystal lattice. On the other hand, if the solute atoms are much smaller than the solvent atoms, they can fit into the tiny spaces, or interstices, between the larger atoms in the crystal lattice. This forms an interstitial solid solution. A prime example is steel, where small carbon atoms occupy interstitial sites within the iron crystal structure. These different arrangements at the atomic level profoundly influence the alloy's properties, affecting everything from its strength to its ductility. Phase diagrams. To understand how alloys behave under different conditions, we turn to phase diagrams. These graphical representations are indispensable tools for materials scientists and engineers. A phase diagram illustrates the relationships between temperature, composition, and the phases present in an alloy system under equilibrium conditions. They allow us to predict what phases will form and in what proportions as an alloy cools or heats up, or as its composition changes. Isomorphous reactions. Let's begin with isomorphous systems. In an isomorphous phase diagram, the two components are completely soluble in each other, in both the liquid and solid states. This means they form a single, continuous solid solution across all compositions. As a liquid alloy in an isomorphous system cools, it solidifies over a range of temperatures, with the composition of both the liquid and solid phases changing continuously until complete solidification. A classic example is the copper-nickel alloy system, widely used in coinage and marine applications due to its excellent corrosion resistance. Eutectic reactions. Next, we encounter eutectic reactions, a critical transformation in many alloy systems. A eutectic reaction involves a liquid phase transforming isothermally, or at a constant temperature, into two distinct solid phases upon cooling. This specific composition, known as the eutectic composition, has the lowest melting point in the system. The resulting microstructure is a fine mixture of the two solid phases, often exhibiting unique properties. Solder, an alloy of tin and lead, is a common example of a eutectic system, valued for its low melting point and excellent wetting characteristics. Eutectoid reactions. Similar to eutectic reactions, eutectoid reactions occur entirely in the solid state. Here, one solid phase transforms isothermally into two new solid phases upon cooling. This transformation is particularly important in the heat treatment of steels. The most famous eutectoid reaction is found in the iron-carbon system, where austenite transforms into ferrite and cementite, forming a lamellar structure called pearlite. This transformation is fundamental to controlling the mechanical properties of steel. Peritectic reactions. Peritectic reactions are another type of invariant reaction in phase diagrams. In a peritectic reaction, a liquid phase reacts with a solid phase to form a new, different solid phase upon cooling. Unlike eutectic reactions, where a liquid transforms into two solids, peritectic reactions involve the consumption of both a liquid and an existing solid to form a new solid. These reactions are often observed in alloy systems with significant differences in melting points between the components, such as in some copper-zinc alloys. Peritectoid reactions. Finally, we have peritectoid reactions, which, like eutectoid reactions, occur entirely in the solid state. In a peritectoid reaction, two solid phases react upon cooling to form a new, single solid phase. These reactions are generally slower than liquid-solid transformations due to the slower diffusion rates in solids, while less common than eutectic or eutectoid reactions. Peritectoid transformations play a role in the microstructural development of certain specialized alloys, influencing their high-temperature performance and stability. Iron-carbon equilibrium diagram. The iron-carbon equilibrium diagram is arguably the most important phase diagram in materials science, serving as the foundation for understanding the behavior of steels and cast irons. This complex diagram maps out the various phases of iron and carbon alloys as a function of temperature and carbon content. Key phases include ferrite, a soft and ductile form of iron, austenite, a high-temperature, non-magnetic phase, and cementite, a hard and brittle iron carbide. Understanding the transformations within this diagram is crucial for controlling the properties of iron-based alloys through heat treatment. Classification of steel and cast iron. Based on their carbon content and microstructures, iron-carbon alloys are broadly classified into steels and cast irons. Steels, typically containing less than 2% carbon, are known for their strength and ductility. They are further categorized into carbon steels, alloy steels, stainless steels, and tool steels, each with tailored properties for specific applications. For instance, stainless steels, with their high chromium content, offer excellent corrosion resistance, making them ideal for kitchenware and medical instruments. Cast irons, on the other hand, contain more than 2% carbon and are characterized by their excellent castability and wear resistance. They are classified into types such as gray cast iron, white cast iron, malleable cast iron, and ductile cast iron, each possessing distinct microstructures and properties. Gray cast iron, for example, is widely used for its vibration damping capabilities, while ductile cast iron offers improved toughness and ductility, making it suitable for crankshafts and heavy machinery components. Conclusion: the constitution of alloys is a rich and complex field, where the interplay of atomic arrangement, phase transformations, and processing techniques dictates the macroscopic properties of materials. From the fundamental concepts of solid solutions and phase diagrams to the intricate details of iron-carbon alloys, understanding these principles is key to designing and developing the advanced materials that drive technological progress. We hope this video has provided you with a deeper appreciation for the science behind the materials that shape our world. Thank you for watching.
Heart's a drum that's pounding loud. Thoughts are racing through